In any organization striving for excellence, the ability to enhance processes is central to achieving operational effectiveness. Step 1. Focus on the problem. Imagine a manufacturing company, XYZ Widgets, that produces parts for various industries. Recently, they've noticed an uptick in defects within their production process. To tackle this issue effectively, the team initiates a focused approach. First, they map the entire process flow, from raw material arrival to the final inspection of products. For example, they take the journey of a component, identifying critical stages such as machining, assembly, and quality control. This exercise highlights where defects often emerge, allowing them to visualize how each step interacts with the next and where potential pitfalls lie. Step 2. Collect data. Equipped with a comprehensive map of their processes, the team then shifts to data collection. They define specific metrics that are vital for evaluating each stage. For instance, they decide to measure the distribution of defects per batch produced to see how variables, such as material quality or machine settings, might influence the outcome. By using data collection tools, they capture information on each defect's nature, frequency, and the corresponding process stages in which they occur. This real-time data not only helps in pinpointing issues, but also lays the groundwork for informed decision-making. Step 3. Identify assignable causes. With data in hand, the team turns to identifying assignable causes, factors that contribute to process variability. Using a Pareto chart, they visualize which issues are most prevalent. For example, they discover that 70% of defects stem from a specific machine malfunctioning during the machining phase. By isolating this primary cause, they can begin to address it directly, reallocating maintenance resources to ensure the machine operates optimally. Step 4. Eliminate causes or reduce variability. Armed with insights into the causes of defects, the team now focuses on eliminating them. They opt for a robust design approach, making necessary adjustments to both processes and equipment. For instance, they implement routine checks and preventive maintenance on the identified machine. Additionally, they redesign certain elements of the process to reduce variability, such as standardizing tool setups and employee training procedures, aiming for a consistent output. Step 5. Evaluate results. Having made changes, the team conducts a thorough evaluation of the results. Utilizing the same tools used for data collection, they closely monitor defect rates post-intervention to assess the impact of their improvements. For example, compared to the previous quarter, they find that defects have decreased by 50%. This significant reduction not only enhances efficiency, but also boosts morale across the production floor, as employees see their efforts resulting in tangible improvements. Step 6. Monitor conformance. Finally, the journey doesn't end with the improvements. The XYZ Widgets team understands the importance of ongoing monitoring to maintain these gains. They implement control charts to continuously track process performance and detect any deviations from established standards. For instance, if a new spike in defects occurs, control charts will highlight this variance in real time, prompting immediate investigation and corrective action. To improve our understanding of business operations, we focus on identifying key variables that affect profitability. These variables include price, demand, capacity, and cost. It's essential to map out processes to find defects and identify the underlying problems. By focusing on how these elements impact ROIC, return on invested capital, we can better understand how to enhance performance. To gather data and define specifications for the scooter, we need to focus on the steering support height. This height should be between 79.9 mm and 80.0 mm. If the height exceeds 80 mm, the steering pole will not fit properly. Conversely, if the height drops below 79.9 mm, it may cause the scooter to rattle and wear out more quickly. It's crucial to maintain this measurement to ensure safety and optimal function of the scooter. In a bustling manufacturing facility, the process of producing a new scooter model was in full swing. Engineers had gathered around a table, discussing the key variable, the steer support height. This measurement was critical, as it directly influenced the scooter's stability and user satisfaction. As the engineers delved into the data, they recognized that some variation in the measurements was to be expected. After all, variations were an inherent part of any manufacturing process. They recalled previous projects where minor fluctuations had not led to significant issues. For example, during the production of a bicycle, slight variations in frame height had only led to minor adjustments in seat positioning, which were easily manageable. However, this time they knew they had to approach the analysis with caution. They recalled the lessons learned from past experiences. Not all variation is problematic. A small range of differences in steer support height could be acceptable. But they understood that too much variation could indicate a deeper issue in the production process. This measurement process is vital, one engineer noted, pointing to a graph displayed on the screen. The graph illustrated the distribution of the steer support heights over time, with some points lying far outside the acceptable specifications. If our process isn't capable of maintaining control, we may end up with a product that isn't safe. They acknowledged the crucial point that the process is not capable when defects occur frequently. There had been instances in the past where the output had strayed too far from the intended specifications. For instance, a batch of scooters had to be recalled because the steer support height was too low, leading to compromised stability. To ensure quality, they decided to implement tighter controls and possibly automation in measuring the heights. With their newfound understanding of the data and the importance of maintaining strict specifications, the engineers felt confident in their approach. They were excited to refine the process, ensuring that each scooter not only met safety standards but also exceeded customer expectations. As the meeting concluded, they turned their attention to the task ahead, optimizing the production process and ensuring that every scooter was a testament to their commitment to quality and safety. In that moment, they weren't just engineers. They were custodians of a brand's promise to deliver excellence. In measuring quality, we focus on two key limits: the lower specification limit, LSL, and the upper specification limit, USL. These limits define the acceptable range of a product's characteristics. The LSL is the minimum acceptable value. Anything below this limit is considered a defect. On the other hand, the USL is the maximum acceptable value. Values above this limit are also defects. Values that are within the USL and LSL are of good quality. Values that are outside the USL and LSL are defective. This process allows us to measure quality indirectly by analyzing defect rates. By collecting data and observing how many values fall within the specification limits, we can assess the overall quality of our processes. In process management, we often need to understand how well a process performs. One important measure is process capability, CP. This metric helps us see how well a process can produce products within specified limits. Natural process variability is the inherent variations in a process. It is represented by a bell curve, which shows how products can vary around a central value. There are two limits. 1. Upper specification limit, USL, the maximum acceptable value. 2. Lower specification limit, LSL, the minimum acceptable value. CP is given to us as the difference between USL and LSL divided by 6 sigma, the natural variability of the process. The CP measure assumes that the process mean can be easily centered within the specification limits. This means the average outcome of the process should ideally sit in the middle of the acceptable range. When we talk about improving skills, it's important to focus on how we measure our performance. In the example of shooting, we look at two groups of shots. On the left, we see a cluster of shots in a tight area. This means that the shooter is consistent. They hit near the target center. On the right, the shots are spread out more widely. This indicates that the shooter is less accurate, hitting the target center less often. To improve performance, we need to look at the concept of variability, which is represented by the standard deviation. It's easier to adjust the average or mean score than to change the spread of the shots. By reducing variability, shooters can achieve a more consistent performance. Focusing on reducing variability helps us become better at what we do. In understanding defect rates, it's important to grasp their significance in quality control. Defect rates are challenging to measure, especially when defects are infrequent. This makes tracking them difficult. We often look at the distribution of the key variable. This involves comparing it to specification limits. By doing so, we gain insights into how to reduce defects. We can focus on targeting the mean, altering the variation, or both. Measuring the key variable is critical. It's straightforward when using control charts. These charts help visualize how the variable behaves. However, sometimes we cannot assess conformance using a simple continuous variable. In these cases, we resort to using defect rates as a measure of process capability. This method helps maintain quality, even when direct measurement of defects isn't possible. Chian recommended a capability index, CP, of 1.33, which corresponds to 4 sigma quality. This standard helps us assess how well our processes perform. At Motorola, a leader named Bill Smith took this a step further. As the vice president of the land mobile products sector, he noticed something important in 1986. He realized that pushing for greater quality, specifically aiming for 6 sigma, was the way forward. However, this pushes us to consider 2 critical factors. 1. The types of defects. We must look at what defects exist in our processes. This helps us understand our weaknesses. 2. Improvement efforts. It's crucial to evaluate how effectively we are working to reduce these defects. Bill Smith pointed out a common issue. Many people underestimate the long-term benefits of a well-designed system that focuses on minimizing defects. His insight focused on the big picture and how important it is to think long-term about quality improvement. If you enjoyed this content, please consider liking and subscribing. Thank you.